Okay, let's unpack this. We've all been there, right? You spend hours, maybe days, writing really detailed documentation, Confluence pages, GitHub readmes, internal stuff, only for your colleagues to immediately slack you the exact question you just answered, like 5 times over. You start feeling less like an engineer and more like this perpetually interrupted, really inefficient human search engine. It's maddening.
It really is.
This pain point is pretty much universal, I think, but our source material for this deep dive gives a perfect kind of high-stakes example from Taranis Tech. They do precision agriculture intelligence, lots of complex computer vision stuff.
Right, sophisticated tech.
And Avi Klayman, one of the veterans there, he was basically the go-to guy for all the legacy knowledge, the keeper of the old ways. But it meant he was constantly getting interrupted. We're talking 4 or 5 times every single day, just answering basic questions, stuff that was documented.
Even though he'd written it all down in Confluence.
Exactly. Painstakingly written out.
Right.
But the core issue wasn't the existence of the docs, it was retrieval. People either couldn't find them, or maybe they just didn't even realize they existed, which led to, massive internal friction, loads of wasted time.
And that frustrating reality, that sort of internal knowledge chaos you get when things scale across different tools, that's really the catalyst for what we're diving into today.
So what's the mission then?
Well, what's fascinating here is that this Taranis scenario, it really represents the failure mode of how we try to manage institutional knowledge, especially now with remote work and distributed teams. Docs get fragmented everywhere. Confluence, GitHub, Slack, emails, and traditional keyword search, it just can't keep up. It doesn't understand meaning. So our mission today is to really dive deep into the specific, detailed roadmap Taranis actually used to tackle this chaos. They built an internal chatbot, a proprietary one, powered by Retrieval Augmented Generation, or ARGI. And this isn't just theory, right? This is a production-ready system they built, designed specifically to query their own siloed data sitting in Confluence, GitHub, and even those messy Slack channels.
Okay, so the outcome we're really focusing on here is the detailed how. We're going to analyze the specific implementation steps they took. Everything from like the initial proof of concept using open source tools like LangChain.
Which is huge.
Yeah, and in that absolutely critical switch they had to make for enterprise production using services like MongoDB Atlas Vector Search. And crucially, the specific engineering tricks, the innovations they needed to actually solve the biggest AI challenge, stopping those, notorious hallucinations.
Yeah, made up answers.
Exactly. And preventing that context fragmentation you get when dealing with sensitive internal business data. That promise of grounded, accurate, citable answers, that's the core insight we're chasing today. Because honestly, that's the only way you're going to build trust in an internal AI system like this.
Absolutely. People need to know where the info came from.
So let's start at that basic architectural fork in the road. If the goal is simply answering internal questions using existing documents, why can't we just point a classic large language model, a big foundational generative AI model like GPT-4 or Claude at our internal Confluence links and just tell it to figure it out? What's the fundamental immediate blocker there? Why doesn't standard GenAI work for proprietary stuff?
That's a really important question, and it gets to the heart of what these foundation models are. Classic generative AI models, they're incredibly powerful, right? Huge predictive engines, but they're essentially static knowledge bases.
Static, okay.
Yeah, they only know what they were trained on, which is almost always public data. And that training data has a cutoff date, often months, maybe even years in the past. So if you ask one of these models about, say, Taranis' specific deployment procedures for their internal system, or the unique naming convention they use for their legacy parts inventory.
It had no clue.
Exactly. It has zero idea. That information was locked away inside Taranis' private network. It never saw the light of day during public training. The models are fundamentally walled off from your private, internal, corporate knowledge base.
And I guess trying to bridge that gap, trying to teach it about those legacy parts, that's probably ridiculously hard. If Taranis did want that classic model to know about their stuff, what would they even do? And why are those options basically like non-starters for a company that's actually moving fast?
Right. Well, they'd face 2 main options, and honestly, both are extremely unappealing. Option 1. You try to cram all the necessary context, all the relevant bits from your documents into the initial prompt you send the model. We call that the context window.
Jumping the prompt.
Pretty much. For a really simple question, maybe you can paste in 2 relevant paragraphs and it works okay. But what if the question needs info from like 5 different Confluence pages. That prompt suddenly becomes massive. You hit token limits, it gets super unwieldy, and maybe worst of all, the cost of every single question just skyrockets because you're sending so much text back and forth.
Okay, not practical. What's option 2?
Option 2 is even worse, frankly. You could try to actually retrain or maybe heavily fine-tune the entire underlying foundation model using your own proprietary data. The source material is very clear on this. It notes that training or fine-tuning these massive models is very expensive.
Like, how expensive are we talking?
We're talking compute costs easily in the tens, maybe hundreds of thousands of dollars. Depends on the model size, how much data you have. Plus, it's incredibly time-consuming. You need specialized MLOps teams to manage it. And here's the real killer. The moment you finish retraining, that knowledge is static again. If Taranis updates a definition for a legacy part the very next day, your freshly fine-tuned, very expensive model is already out of date. The cost is just prohibitive, and the time lag completely defeats the purpose. You need current, up-to-the-minute answers in a fast-moving business. Retraining just can't keep up.
Okay, so this brings us squarely to RAG, Retrieval Augmented Generation. This is the star of the show, you said, because it offers a way around this, an efficient compromise. How does this specific mechanism bypass that huge cost and time sink of full model retraining, but still let the AI tap into the freshest internal docs?
RAG is really quite an elegant solution, and yeah, efficient is the key word. It basically treats the foundation model like a brilliant but maybe slightly forgetful intern. It says, look, we don't need to train you to know everything permanently in your weights. We just need you to be really good at reasoning about information and synthesizing answers based on information we give you right now at query time.
Okay, so it's providing the info on the fly.
Exactly. RA leverages the raw intelligence and the conversational ability of the LLM, but it forces it to first consult a secondary, up-to-date, customized index of your specific internal data before it even tries to generate a response.
Right.
It's essentially like giving the LLM a highly targeted, real-time cheat sheet that's specific to the user's immediate question.
That distinction is super important. The real innovation isn't the LLM itself, it's the pipeline, the architecture that makes this cheat sheet process happen. Let's break down the mechanics, because this 3-step flow, embedding, query and search, and grounding this is exactly what the Taranis team built. So step 1, embedding. What's happening there?
Right. So the first stage is all about ingestion, getting your knowledge into the system. You take all your raw text data, every Confluence page, every GitHub README, every relevant Slack message perhaps, and first you typically break it down into smaller pieces, manageable chunks.
Why break it down?
Well, you need chunks that are semantically cohesive. They should be about one topic ideally, but also small enough to work with efficiently later. Taranis, for example, likely used a chunk size somewhere around, say, 512 tokens. Maybe with a little bit of overlap between chunks, just to make sure you don't accidentally chop off context right in the middle of an important sentence.
Okay, got it. Chunks. Then what?
Then you feed these text chunks through an embedding API. Taranis used OpenAI's embedding model, probably the text embedding ADA 002 model, which was, and still is, very widely used. It's known for good performance and capturing semantic meaning well.
And that API turns the text into numbers, vectors.
Exactly. It converts the human language text into these high-dimensional vectors, which are just long lists of floating point numbers. You can think of it like giving every single chunk of text its own unique set of GPS coordinates, but in a massive multi-dimensional meaning space.
Hold on, let's pause on that vector idea for a sec, because this is where I think a lot of people's eyes glaze over. What does it mean that these numbers capture meaning? How does a list of numbers represent like the concept of server connections?
Yeah, it's a fair question. It sounds a bit like magic. But the core idea is that the mathematical distance between two vectors in this high-dimensional space directly correlates to how semantically similar the original text chunks are.
Okay.
So if one text chunk is about troubleshooting server connections and another one talks about diagnosing network issues on the main server, even if they use different words, their vectors will be numerically very close together in that space. They're conceptually related.
Where it's something completely different.
Right. A chunk about server connections and another chunk describing, say, HR onboarding policies, their vectors will be miles apart in this meaning space. The embedding model learns to place similar concepts near each other, and this whole collection of numerical vectors, along with the original text, gets stored in a specialized database called a vector data store. This is specifically built to do those super fast distance calculations needed for searching, which, spoiler alert, is what Taranis eventually used MongoDB Atlas vector search for.
Gotcha. So this numerical representation, this meaning space, is what lets the system find stuff based on concepts, not just exact keywords like, a general plus F search or a basic SQL-like query. Okay, so the knowledge is vectorized, it's indexed in this special store. Now we get to step 2, the query and search phase. A developer finally asks the chatbot a question in plain English.
Right. So a developer types in, how do we troubleshoot the legacy widget connection on our latest staging build? First thing that happens. That question itself gets converted into its own vector using the exact same embedding model that was used for the documents. Consistency is key here.
Same model, okay.
Then the RAG system performs a lightning-fast vector similarity search across the entire vector data store. It uses clever algorithms, things like HNSW, hierarchical navigable small worlds, which is what MongoDB Atlas uses under the hood, to very efficiently find the stored document chunks whose vectors are numerically closest to the question's vector.
And because it's based on meaning.
Exactly.
Oh.
Because the search is based on semantic similarity, it efficiently finds chunks discussing legacy widget connection issues, even if the developer phrased the question slightly differently, maybe using synonyms like old component diagnostic steps.
Right.
It understands the intent behind the words, not just the words themselves.
Okay, that makes sense. It finds the relevant cheat sheet pages. Which brings us to step 3, grounding. You said this is the crucial defense mechanism against bad information.
Yeah.
The part that builds trust.
Precisely. This is where RAG really shines, compared to just asking a raw LLM. The system retrieves those top few relevant document chunks, the results of that similarity search, and it passes those chunks, which we call the context, directly alongside the original user question to the external GenAI model, like GPT-4.
So it's not just asking the question, it's giving it the relevant text too.
Right. The system effectively injects a very specific prompt into the LLM. It's basically saying, okay, LLM, here's the user question. Now, here are the specific verified facts retrieved directly from our company's up-to-date internal documents. Retrieved context chunk 1, retrieved context chunk 2, etc. Your job is to generate a concise and accurate answer only using the facts provided in this context. Do not make things up. If the answer cannot be found solely within this provided context, just say you don't have enough information from the document.
That instruction, that constraint to only use the provided context, that's the key thing, preventing the AI from just defaulting back to its old static public knowledge base and potentially just inventing an answer.
Hallucinating.
Exactly that. It forces the LLM to act like a summarizer and synthesizer of the provided information, rather than a generator pulling from its vast but potentially irrelevant or outdated internal knowledge. The practical benefits here are massive, and they directly solve the problems Avi was facing back at Taranis.
Like what specifically?
Well, first, RG systems can and should automatically provide the source of the answer. Because you know exactly which document chunks were used as context, you can easily include citations, maybe a link back to the specific Confluence page or the GitHub Reatomy the AI used. This gives you verifiability. Engineers love this. They can click the link and check the source themselves. It builds trust immediately.
Yeah, traceability is huge. Definitely. And second, and this is probably the primary defensive benefit, it fundamentally helps avoid those notorious AI hallucinations. By forcing the answer to be strictly grounded in the company's real, custom, verified information, RA turns the powerful LLM into a highly effective, safe summary engine for your own proprietary data.
Okay, so moving from the theory of RA to actually deploying it, the Taranis team did something really smart, a fantastic best practice. They didn't try to reinvent the wheel completely. They didn't start coding from a blank file. They wisely found and leveraged an existing open source repository. I think it was called our Chatbot with Confluence, giving them a running start.
Yeah, that's right. And using that starting point, it probably accelerated their initial development significantly, saved them weeks, maybe even months of just setting up the basic plumbing and configuration. The core components were pretty much established right away.
What were those core components in that initial setup?
Well, they relied heavily on LangChain. LangChain is really the crucial middleware here, the orchestrator. It's important to understand LangChain isn't an AI model itself, right? It's more like a framework, a toolkit that helps you chain together all the different pieces of the RAD pipeline.
Okay.
So LangChain handles a lot of the tasks we just talked about. It provides the pre-built document loaders for pulling data from sources like Confluence and GitHub. It helps manage the text chunking strategy, using tools like its recursive character text splitter. And it makes it relatively easy to connect your vector store, whatever you choose, to the OpenAI LLM through these defined structures they call chains. It simplifies building the whole flow.
And for the user interface, that initial version.
For the UI, they started with Streamlit, which is honestly the absolute go-to standard if you want to quickly spin up a functional interactive web app for a data science or AI project. It let them build a proof of concept interface really fast so they could immediately start testing on retrieval quality, tweaking things before needing to commit to a more complex final front end.
Smart. Get feedback early.
Exactly. And for stability, right from the get-go, they Dockerized the project, put the whole thing in a container. This ensures that the environment, all the libraries, the Python versions, everything is consistent, whether they're running it on a developer's laptop or deploying it to a server. Absolutely critical step if you ever want to move a prototype towards actual deployment.
So they handled the initial setup, putting in API keys, maybe translating some instructions, getting the Streamlit app running locally. But as often happens, that local setup probably hit a wall pretty quick when they started thinking about real usage, about scaling it up.
Oh, absolutely. A local prototype is one thing, but the architecture had to evolve pretty rapidly as they started thinking about production use, multiple teams using it across different knowledge domains within the company.
And this feels like the critical transition point, the production leap. The source material mentions that the initial vector store used in that open source project they started with was Chroma, or ChromaDB. Now, Chroma is a fantastic tool, right? Great for local experiments, for trying things out on your own machine. So why was it immediately seen as insufficient for what they needed, a high availability, high concurrency, enterprise-grade production system?
Yeah, that's a fundamental architecture question, moving from dev to prod. Chroma is brilliant for getting started locally. It's often file-based or runs easily in memory. But production environments have totally different demands. You need serious reliability, you need scalability, and ideally, operational simplicity. And often, only managed cloud services can really provide all of that reliably.
What specifically breaks down with something like Chroma in production?
Well, when you start talking about enterprise knowledge, which could mean hundreds of thousands, maybe millions of document chunks and potentially hundreds of engineers hitting the chatbot simultaneously with queries, you need guarantees. Chroma, especially in its earlier versions or simpler configurations, can sometimes struggle with high concurrency. Requests might start queuing up. Latency can spike unpredictably. More critically, though, an enterprise system needs things like built-in high availability. If one server node fails, another takes over seamlessly. It needs data sharding to spread the load for better performance. It needs robust disaster recovery mechanisms, automated backups. Managing all of that yourself for a self-hosted vector database like Chroma, ensuring its uptime, guaranteeing data consistency, handling backups and restores. That requires significant MLOps overhead. A dedicated team, basically. And that's a cost and complexity Taranis, quite wisely, decided they wanted to avoid.
Right. They wanted to focus on the application, not managing database infrastructure. So to get that production readiness, that robustness and scalability, they needed a different solution. And they chose MongoDB Atlas Vector Search. Why was that the clear production choice for them? What made it fit?
The primary reason cited in the source was actually organizational, which is often a huge factor in tech choices. They already had positive experience using MongoDB elsewhere in their existing tech stack.
Familiarity.
Exactly. That's massive. Choosing tools that integrate cleanly with your existing data infrastructure, your existing monitoring, your security protocols, it simplifies deployment hugely. It simplifies maintenance. And crucially, it means you can often leverage your existing security and governance policies that are already in place from MongoDB. With Atlas Vector Search, they could store their vector index right alongside their other operational data if they wanted, all within the same managed platform.
And technically, did it meet the performance needs?
Yes. Technically, MongoDB's vector search capabilities, which are powered by that HNS-W index algorithm we mentioned, offered the speed and the scaling they needed. It's designed to handle the high throughput, the large number of documents, and the concurrent queries they expected from a company-wide internal tool without the performance degrading. It ticked the boxes for both operational simplicity and technical capability.
Okay, so they settled on the production stack. They implemented this MongoDB ARAG architecture, which kind of splits the whole process into two distinct scalable pipelines. Let's detail the data ingestion pipeline first. Now that they were using MongoDB Atlas as the vector store, how did they actually get that massive collection of Confluence documents transformed and loaded into this searchable, indexed vector database?
Right. The ingestion process became a more formalized, probably periodic pipeline. They'd use LangChain's Confluence loader, configure it with the right credentials, and tell it which specific Confluence space IDs to pull from, R&D support, et cetera. The key steps were pretty well defined by this point.
What were they?
Okay, so first, obviously, extract the raw text from the Confluence pages. Second, break that text into those consistent chunks we discussed again, thinking about maybe 512 characters, maybe a bit of overlap. That's a pretty standard practice. You choose that size because it's generally large enough to capture meaningful semantic context, but it's also small enough that the vector search can return several relevant snippets later without completely overwhelming the LLM's context window limit.
Makes sense. Keep it manageable.
Third, send those text chunks off to the OpenAI embedding model DAVA002 to get back those high-dimensional vector representations. And then finally, step 4, store those vector representations and, crucially, pair them with the original text chunk and some critical metadata, which we'll talk about a lot more soon. Store all of that and index it within MongoDB Atlas. And that index isn't like a simple list. It's specifically that optimized HNSW structure designed for really rapid vector similarity searches. That's what ensures that even when the system scales up to thousands or millions of documents, the search time stays down in the milliseconds range. Fast retrieval is key.
Right. So that's the pipeline, constantly keeping the knowledge base fresh in MongoDB. And once that ingestion process is done, or running periodically, we see the architecture of the query processing pipeline kick in whenever a user actually asks a question.
Exactly. When a developer types dev-ask, how do I reset the staging DB into Slack, the system executes that sequence we laid out earlier. First, the question itself gets embedded into a vector. Second, the system performs that semantic similarity search against the index data in MongoDB Atlas, retrieving the most relevant document chunks the context. And third, it passes that context, along with the original question, to the OpenAI language model, like GPT-4, to synthesize a concise, human-readable answer. The crucial point here is really the reliance on MongoDB Atlas vector search for that retrieval step. Its performance and scalability are what make the entire RAG cycle efficient enough to feel responsive for real-time internal use, handling the kind of volume and data complexity that a simpler local tool like Chroma just couldn't sustain in a real production environment.
Okay, so the basic architecture is up, running on MongoDB Atlas. But as soon as this chatbot moved from just a prototype into actual internal use, the team smacked into its first major practical difficulty. The kind of problem you only really uncover when you hit the messy reality of real-world data. An accuracy problem started showing up. What was happening?
Yeah, the chatbot sometimes started mixing up data from different Confluence spaces. It was leading to answers that were either irrelevant or worse, just plain confusing.
How so? What's an example?
Well, this is kind of the curse of consolidating all your knowledge in one place, right? The semantic search was actually working too well, in a way, but without enough constraints. For instance, think about a term like deployment schedule. That phrase might appear in the R&D Confluence space, where it refers to, technical staging practices, code freezes, that kind of thing.
All right, engineering stuff.
But the exact same phrase, deployment schedule, might also appear in the support team's Confluence space, where it refers to communicating feature rollout dates and timelines to customers. Totally different context.
Ah, I see the problem.
So if a developer asked a technical question about the deployment schedule, the semantic search might find the engineering page, but it might also find chunks from the support page because, hey, the vectors for deployment schedule are numerically similar. It doesn't inherently know the developer only cares about the R&D context. The result: the retrieved context chunks get mixed up. The LLM sees conflicting information. Maybe one chunk talks about Jenkins jobs, the other talks about customer email templates, and it either tries to awkwardly jam them together into a fragmented answer, or it just defaults to the wrong domain entirely, giving the developer customer support info. Utterly irrelevant noise.
Okay, that's a serious issue. It undermines trust immediately if you get answers from the wrong department. So that's where the metadata solution came in. This sounds like a fantastic example of using the database layer itself, the vector store's capabilities, to really improve the AI's accuracy and relevance. They made a critical decision, adding a custom property domain, was it, to the metadata stored right alongside each vector in MongoDB.
Correct. That was the key insight. Vector stores like MongoDB Atlas are extremely flexible. They don't just store the vector, they let you attach any arbitrary key value pairs, any metadata properties to that vectorized data chunk. So Taranis did something clever. They mapped their internal Confluence space keys, which were probably cryptic acronyms like RD for R&D, AAKC for their agriculture knowledge cluster, STA for support, maybe ROD for product, OPS for operations, etc. They mapped these to clear, simple, user-friendly domain tags, strings like ARND, ag, support, product, and ops.
Okay, simple mapping.
And then during that ingestion pipeline we talked about, every single text chunk, as it was being processed and stored, got tagged with the correct domain based on which Confluence base it came from.
And how did just adding that simple tag translate into better search results? How did it fix the mixing problem?
It provided a really powerful pre-filtering mechanism. They adjusted the Streamlit UI, the chatbot's front end, to include simple radio buttons. So now, before a user even types their question, they could just click to select their desired domain. I'm interested in R&D, or I need info from support.
Ah, the user specifies the context.
Exactly. And critically, that selection wasn't just for show. It was translated directly into a pre-filter query that was executed by MongoDB Atlas before the potentially expensive vector similarity search even started.
So it narrows the field first.
Precisely. The database first says, okay, only look at documents that are already indexed with the chosen ARN domain tag. It restricts the search pool dramatically. And then only within that pre-filtered set of R&D documents does it run the vector search to find the chunks most similar to the user's question. This completely eliminates that cross-domain contamination issue. It drastically reduces the noise, ensures the LLM is only ever shown relevant domain-specific information, and makes the answers much, much more accurate.
That makes a ton of sense. Filter first, then search semantically. They also use this metadata tagging opportunity you mentioned to add another property source, noting the original document URL or the page source for every single chunk. We touched on this earlier, saying it becomes crucial later. Why was tracking that little fragment back to its original home document so vital? What did that enable?
Yeah, adding the source property at the same time as the domain was really crucial engineering foresight. It was necessary because, remember, we broke the knowledge down into these small, maybe 512 character chunks for efficient vector storage and retrieval. But if you only store the chunk and its vector, that chunk becomes an island. You lose the connection to where it came from.
Right, it's just floating text.
By adding the source property storing the original Confluence page URL, or the GitHub file path for every single chunk, you establish a clear, traceable lineage. You know exactly which parent document this piece of text belongs to. And as we'll see in a bit, that lineage, being able to say, this chunk came from that specific page, becomes the absolute backbone of their most effective accuracy improvement later on. It lets them reconstruct the original context.
Okay, interesting. So domain filtering fixed the cross-department issue. But beyond just refining the search within Confluence, they also quickly realized that Confluence, even with all its pages, wasn't the sole place important knowledge lived. They needed to expand the chatbot's knowledge base to capture expertise that was siloed elsewhere.
Yeah, that's a common realization. Documentation rarely lives in just one system. They identified at least two other major, previously untapped knowledge silos within Taranis. First one, GitHub readme files.
Ah, the classic README.
Exactly. So much crucial information often only lives there. Project setup guidelines, specific command line instructions to run something, troubleshooting steps for common errors, local development environment configuration. It's often right there in the readme.md file within the code repository itself.
So how do they get that in?
They again leveraged LangChain's fantastic ecosystem of integrations. They used LangChain's GitHub file loader, configured it to point at their specific internal GitHub repositories, and told it to specifically target and pull in the content of the readme.md file from each designated repo. This text data was then chunked, embedded, and ingested into MongoDB, just like the Confluence data. They probably manually tagged this data with the run domain, since it's mostly developer-focused, and crucially, the metadata included the full GitHub URL of the readme file as the source property.
Makes sense. Capture the dev knowledge at the source. What was the second, maybe more complex source they added?
The second one was Slack, specifically public Slack channels.
Ooh, okay. That sounds messy.
It is messy, but the source notes that surprisingly useful things often get discussed and resolved there. Quick solutions to problems, critical architectural decisions debated and finalized in a thread, little nuggets of wisdom. But that knowledge gets buried incredibly quickly under the sheer volume of daily chat messages.
So how do you even approach ingesting that? Did they connect live?
It sounds like they started with a data dump approach first. They likely exported the history from relevant public Slack channels, probably as JSON files or something similar. Then they used another LangChain tool, the Slack directory loader, which is designed to parse those kinds of Slack exports. They'd run that loader over the dump, extract the messages, maybe do some cleaning, chunk them, embed them, tag them with a Slack domain perhaps, add the message timestamp and channel info as metadata, including a permalink URL as the source, and load them into the MongoDB vector store.
Wow, okay, so Confluence, GitHub, READMEs, Slack messages. This really highlights the incredible versatility of RAG, right? The RAG advantage, you could call it this, data source agnosticism. It almost doesn't matter where the text comes from originally.
Absolutely. That is one of the core takeaways here. The underlying LLM, the vector embedding model, they don't really care about the original format. Was it a nicely structured Confluence page, a markdown file from GitHub, a snippet of conversation from a Slack thread? As long as you can extract the raw text content, you can embed it into a vector, store it in your index alongside relevant metadata, and make it searchable. RG itself is incredibly flexible about inputs. However...
There's always a however.
Yeah. Integrating conversational data, like Slack, introduces a whole new layer of complexity that you absolutely have to address head-on if you want it to be genuinely useful and not just add noise. You can't just treat it exactly like static documentation.
Okay, let's dive into that complexity now, because just ingesting a Slack dump, treating it like static text, that sounds like it would create problems beyond just needing domain filtering. The source hinted at two major issues, specific to conversational data like Slack. What were they? Fragmentation and freshness.
Precisely. Those are the two big headaches with chat data. First, the fragmentation issue gets way worse than with structured docs. Think about it. A solution described in a Confluence page might be neatly contained on, well, a single page, but a solution discussed in Slack, it might span 10 different messages scattered across an after-named thread, maybe with interruptions or side conversations in between.
Right.
Standard chunking and retrieval methods, where you just grab the top and most similar chunks, might only retrieve one of those 10 messages, completely missing the vital context provided by the messages that came before or after it in the thread. You might get the answer, but not the question, or vice versa. Looking at message threads helps a bit, but stitching that conversational context back together accurately during retrieval is a real challenge. It remains a headache.
Okay, so getting the whole answer from a chat thread is hard. What was the second issue? Freshness.
Yeah, the second challenge, and arguably the much bigger one for Slack data, is data freshness, or rather the lack of it. Slack channels are absolutely littered with outdated conversations, deprecated advice, debugging attempts for problems that were later solved differently or just failed, discussions about features that got canceled, you name it.
All the historical baggage.
Exactly. So a user might ask a question today like, how do I fix bug X? The semantic search might find a conversation from 18 months ago where people were discussing bug X because the vectors are very similar, but maybe that entire system component was completely rewritten 6 months ago, and the advice from 18 months ago is now totally wrong, maybe even dangerous if applied to the current system. The RAG system, just doing basic semantic search, might retrieve that old deprecated context. It provides an answer that's technically accurate based on the text it found, but practically useless or actively harmful for the developer today.
So a simple vector similarity search fails here because it just looks for the closest meaning. It doesn't care when that meaning was relevant. The vectors for how to fix bug X in 2022 and how to fix bug X in 2024 might look almost identical to the embedding model, but only the 2024 answer is actually correct now.
That's exactly the problem. It highlights a fundamental limitation of relying solely on semantic similarity for high-velocity, rapidly aging data like chat logs. To truly integrate Slack effectively and reliably, the Taranis team would have recognized or quickly discovered that their standard semantic search retrieval needed augmentation. They would need to implement a custom ranking algorithm for Slack results. One that doesn't just look at semantic similarity, but actively integrates a temporal factor, you could call it a freshness score, right into the retrieval process itself.
How would that work? Weighting based on time.
Yeah, essentially. This custom algorithm would need to look at the timestamp metadata that they wisely stored alongside each Slack message chunk during ingestion. When performing the search specifically within the Slack domain, the system wouldn't just grab the top n semantic matches. It would need to perform a more complex, weighted calculation. Semantic similarity score would still be important, but it would be balanced against the document's age. Newer messages would get a relevance bonus, while older messages would get a penalty.
Unless the user specifically asked for old info.
Right, good point. You'd need exceptions. If the search query itself contains explicit time constraints, like, tell me about the 2021 migration plan, then the temporal penalty for older docs should probably be ignored or adjusted. But for general queries, you'd want to heavily favor recent information. This is definitely getting into more advanced data engineering, building custom scoring logic on top of the basic vector search. But it's absolutely crucial if you want to make Slack knowledge a reliable, trustworthy source for your RAG system, rather than just a potential source of dangerously outdated advice. While the initial Taranis implementation managed to ingest the Slack data, building out that really effective temporal ranking algorithm is the necessary next step for truly leveraging conversational knowledge safely and effectively at scale.
All right, so they've filtered by domain. They've started pulling in diverse sources like GitHub and Slack, even acknowledging the complexities there. But now we arrive at the second, and honestly, maybe the most inventive accuracy hurdle they had to clear. Even with domain filtering working perfectly for Confluence and GitHub, and maybe setting aside the Slack freshness issue for a moment, the answers derived just from Confluence and GitHub pages were still sometimes coming back fragmented or incoherent. What was causing that?
Yeah, this one comes right back to that initial retrieval strategy, how they were getting the context for the LLM. Remember, in the first iteration of their RAG pipeline, they were using the semantic search to retrieve, let's say, the top 3 most relevant text chunks from the vector store. And then they'd feed those 3 chunks together as the combined context to the LLM.
Right. Top 3 semantic hits. Seems logical.
It seems logical, but the core issue, as we kind of foreshadowed earlier, was that those top 3 semantically similar chunks often originated from 3 completely different source documents. Maybe one chunk came from Confluence page A, the second from Confluence page B, and the third from a GitHub re-env.
Okay. Different sources contributing to one answer context.
Exactly.
Yeah.
And this is where the fragmentation happened. Let me give you a concrete example. Imagine a developer asks the chatbot, what is the exact procedure for resetting the production database environment? A pretty critical question, right?
Very critical. Don't want to mess that up.
Definitely not. So the semantic search runs. It might retrieve chunk 1, which is maybe a paragraph discussing the team permissions required to even attempt such a reset. And this paragraph lives on Confluence page A, the database access policy page. Chunk 2 might be the snippet containing the actual technical command you need to type to execute the reset. And this lives on Confluence page B, the production environment runbook. And chunk 3 might be a high-level summary paragraph from a GitHub readme file, page C, talking about why resetting production is dangerous and should only be done as a last resort.
Okay, all 3 chunks are related to the question.
They are. Semantically, they all relate to resetting production database. But they come from 3 different places with slightly different focuses. Now, you feed these 3 disparate chunks together to the LLM. The LLM's job is to synthesize an answer based only on that context, so it tries its best to weave these 3 fragments together.
And the result is?
The result is often an answer that, while containing bits and pieces of truth, completely lacks a cohesive, step-by-step, actionable narrative. It might jump from permissions to a warning to the command without clear flow. Or worse, it might inadvertently mix details. Maybe it pulls the procedure for the staging database, because a chunk about that was also semantically similar, but combines it with the permissions needed for production. The final answer becomes incoherent, potentially contradictory, or in the worst case, dangerously misleading, because the context itself was fragmented and mixed across multiple original sources.
Yeah, that's a huge problem for trust and usability. So they had to radically change their retrieval strategy again. They moved to what the source calls the single source solution. This sounds like a really clever engineering innovation tailored specifically to fix this RI context problem. It's designed to absolutely guarantee a cohesive context for the LLM. What are the 2 steps that define this specific solution? How did they implement it?
It's actually a really elegant 2-step process, building directly on the work they already did with metadata. Step 1. They performed the initial semantic vector search just like before, but with one critical change. Instead of retrieving the top 3 or top n chunks, they retrieved only the single topmost relevant chunk. Just one. The absolute best starting point that semantically matches the user's question.
Okay, find the best single fragment first. Then what? Step 2.
Step 2 is where the magic happens, the real retrieval augmentation. Using that crucial source property that they diligently tagged every chunk with back in section 3, the property identifying the exact URL or file path of the original document, they immediately queried the vector store again. But this second query was completely different.
How so?
This second query didn't use vector similarity at all. It was a metadata filter query. It basically instructed the database. Find and retrieve for me all other chunks in the index that share the exact same source property value as the single chunk we just retrieved in step 1.
So if the top chunk came from Confluence page B, the second query says, give me every chunk from page B.
Exactly. That's precisely it. It uses the source of the best initial match to pull in the entirety of that original document, just broken down into its index chunks.
Wow. So by performing that two-step maneuver, find the best chunk, then find all its siblings from the same source, they guaranteed that the LLM was only ever working with content that originated from one single cohesive document, one Confluence page or one GitHub readme file.
That's the core idea. It moves the RIA system away from trying to synthesize an answer from potentially disjointed fragments and towards summarizing one complete relevant document that, as a whole, is the best match for the user's query.
And the impact on answer quality.
The source takes it pretty clearly. This process drastically improved the answer quality. Because now, instead of feeding the LLM these disconnected paragraphs from all over the place, they were providing one full, cohesive document context, maybe a long Confluence page, covering the entire reset procedure from start to finish that was entirely relevant to the initial question. The LLM can now rely on the inherent narrative structure, the flow, the completeness of that single original document, which is much closer to how we humans actually use documentation to understand complex procedures. It completely solved the context fragmentation problem.
Okay, that sounds incredibly effective.
Yeah.
But now I have to put my engineering skeptic hat on for a second. Retrieval speed, latency, it's everything in a production chatbot environment, right? Users won't wait 10 seconds for an answer. If you run one query, the expensive vector search, just to get the single most relevant chunk, and then you run a second full query to get all the related chunks from that same source, aren't you basically doubling the database workload? Aren't you introducing significant extra latency with that second query? Seems like it would slow things down considerably.
That is a totally valid concern and a critical question about the performance trade-off involved here. And it really underscores why choosing a robust, optimized vector store like MongoDB Atlas in their case actually matters for implementing these more advanced strategies. The key is to understand the fundamental difference between those two queries they're running. The first query, the one that finds the single best chunk using vector similarity search, that's the computationally expensive one, that requires the database to potentially search across millions of high-dimensional vectors, calculate distances using algorithms like HNS-W. It's inherently complex work even when heavily optimized.
Yeah.
That's where most of the time goes.
Right. The vector math is hard.
But the second query, the one that says, find all chunks where the source property equals confluence.com page 1233, that query is significantly cheaper. Why? Because they wisely tag the source property as standard MongoDB metadata alongside the vector. So that second query isn't a vector search at all. It's a simple, highly optimized, indexed key value lookup.
Ah, like a standard database index query.
Exactly. It's a classic database retrieval operation. Find all documents where this indexed field, source, matches this specific value. Databases like MongoDB are incredibly good at executing these types of filter lookups extremely fast, often in microseconds or low milliseconds, especially if the source field is properly indexed, which it certainly would be.
So the expensive part is finding the needle, the best chunk. But retrieving the rest of the haystack, all chunks from that source, is super fast using the metadata tag.
Precisely. While, yes, there is some fractional increase in overall latency because you're doing 2 round trips to the database instead of 1, the second trip is incredibly quick. The massive gain in answer accuracy and coherence, moving from a potentially useless fragmented answer to a cohesive, genuinely useful one, vastly, vastly outweighs that minimal performance cost. It's a very smart, optimized trade-off, prioritizing the quality and trustworthiness of the answer over shaving off a few extra milliseconds that the user likely wouldn't even notice.
Okay, that makes sense. The second query is cheap because it's just a metadata filter. Now, implementing this complex custom two-step retrieval logic, that sounds like it required going beyond just configuring LangChain with a few parameters. How did they technically implement this custom process? Did they have to modify LangChain itself?
This is where you get into the slightly deeper weeds of framework customization, but it's a common pattern when you need to tailor behavior. LangChain provides the excellent scaffolding, the building blocks, but Taranis needed to customize how one of those blocks worked. They didn't have to fork LangChain or anything drastic like that. Instead, they used object-oriented programming principles. They had to inherit from the existing LangChain class responsible for interacting with their specific vector store, in this case, the MongoDB vector search class provided by LangChain.
Inherit, like creating a child class.
Exactly. They created their own custom class, let's call it Taranis MongoDB single source search, that inherited all the functionality of the base MongoDB vector search class. Then, within their own custom class, they overrode one specific core method, the one responsible for actually performing the retrieval. This would likely be the similarity search function, or maybe a related internal method it calls.
Override means they replaced the original function's logic with their own.
That's right. The original similarity search method in the base LangChain class would just execute the vector search and return the top end result directly. Their new modified similarity search method in their custom class would do something different. It would probably first check a new internal parameter they added, maybe something like single source mode, or true. If that mode is active, the method would execute the standard vector search using the underlying connection, but strictly limit the result set to just the K1, the single most similar document.
Okay, that's the top one.
Then it would extract the source metadata value from that single document result. And here's a custom part. Instead of just returning that single result, it would then execute that fast secondary database query directly on the underlying MongoDB collection object, which the LangChain class would hold a reference to. Something like self.collection.find, metadata.source, retrieved sourceid. This secondary query completely ignores vector similarity. It just pulls back every chunk that shares that exact source identifier. Finally, their overridden method would return the list of all those chunks belonging to the single best source.
Wow. That's a brilliant, really practical piece of software engineering. They took a generic RA tool, found its limitation for their specific need, context fragmentation, and then surgically extended its behavior using standard programming techniques to create a domain-specific expert. An expert that understands the critical need for context cohesion when dealing with complex internal documentation.
Exactly. It's a perfect example of how you often need to blend the power of these generic AI frameworks with targeted custom code to solve real-world business problems effectively.
Okay, so we followed the journey. The chatbot is now pretty accurate. It's grounded in a production-ready vector store like MongoDB Atlas. It's using that clever single-source retrieval to ensure context cohesion. It sounds technically solid. But as we know, technical brilliance is kind of useless if the tool isn't actually used by the people it's meant to help. Taranis clearly understood this. While that Streamlit UI was great for development and testing, the ultimate goal had to be maximum accessibility, meeting the developers exactly where they already live and breathe their entire workday, which is, of course, Slack.
Indeed. You hit the nail on the head. Remember the original problem. It was developers constantly interrupting Avi on Slack with questions. So the solution, to be truly effective, had to be integrated directly back into that primary communication workflow. Only then could it genuinely eliminate the friction of having to stop what you're doing, open a browser, find the right internal portal, try to search.
Right, that whole context switching fatigue developers hate.
Exactly. Developers really don't want to leave their IDE or their main chat application if they don't have to. Every context switch breaks flow.
Oh.
So Taranis' solution was elegant and direct. They implemented a custom Slack/command devask.
The classic slash command. Simple but effective.
It's beautiful in its simplicity and deep integration, isn't it? Developers don't need to switch context at all. They don't need to open a new browser tab. They don't even need to remember a specific URL for the chatbot portal. They just stay in Slack in whatever channel they're already in and type devask followed by their question like devask. How do I configure the test environment for Project Phoenix? Hit enter, done. This approach maximizes adoption because it minimizes friction.
Absolutely. That feels like a massive win for developer efficiency right there. The team can hopefully focus more on actually coding and less on hunting down documentation or waiting for Avi to answer. However, integrating with external platforms like Slack, especially for these interactive commands, often brings its own set of purely technical requirements, completely separate from the AI complexity itself. And the big one is usually latency, right?
That's right. Slack, like many real-time platforms, is pretty strict about the user experience for its interactive elements, like slash commands. To prevent users from just seeing a spinning wheel forever if a command fails or takes too long, Slack imposes a hard timeout. You absolutely must return an acknowledgement response back to Slack almost instantly. Specifically, the requirement is within 3 seconds.
3 seconds? That's not a lot of time.
It's really not, especially when you consider everything that needs to happen for our ARG chatbot. You've got the network latency just to receive the command from Slack. Then you need to embed the question, API call to OpenAI. Then you run the first vector search query against MongoDB Atlas database call. Then you run the second metadata query to get all sibling chunks, another database call. Then you package all that context up and send it to the main LLM, like GPT-4, for generation, another potentially slow external API call. And then you get the answer back and format it. That entire ARG process.
It's definitely taking longer than 3 seconds.
Oh, easily. It often takes 4, 5, maybe even 7 or 8 seconds, especially if the database or the OpenAI API is under heavy load at that moment. There's absolutely no way the full synchronous process could reliably complete within Slack's 3-second window.
So what happens if you don't respond in 3 seconds?
Slack registers the command as a failure. It just times out. The user who typed dvask simply sees an error message right there in Slack, something like, command failed to execute. And that immediately erodes trust in the chatbot. If it fails half the time, people will just stop using it and go back to pinging Avi. They couldn't just tell the developers, oh, just wait 10 seconds, maybe it'll work. And they certainly couldn't ask Slack to change its fundamental rules.
Okay, so they hit a classic integration hurdle. The backend process is too slow for the front-end synchronous requirement. They had to implement some kind of asynchronous processing strategy then. How did they manage to meet that strict 3-second Slack timeout constraint while still letting the lengthy RAG process run its course in the background?
The solution involved leveraging a modern, robust API framework that's specifically designed to handle this kind of thing easily. The source mentions they used FastAPI, and specifically, FastAPI's built-in support for background tasks.
Okay, background tasks. How does that work in practice?
Think of it like a busy restaurant kitchen's ticketing system. When you, the customer, or Slack in this case, place an order with the waiter, our main FastAPI application thread, the waiter doesn't just stand there waiting for the kitchen, the slow RAG process, to fully cook the meal before telling you they got the order. That would be terrible service.
Right, you take the order, give it to the kitchen, and move on.
Exactly. The sequence here is perfectly orchestrated using FastAPI. 1, the user triggers the dvask command in Slack. 2, FastAPI receives that incoming request. 3, the very first action the FastAPI application takes is to send an immediate, instantaneous acknowledgement response right back to Slack. Just a simple HTTP 200, okay, maybe with a payload like text. Got it. Processing your query now. I'll post the answer back here shortly. This takes milliseconds.
And that satisfies Slack's 3-second requirement.
Instantly. Slack is happy. The user sees immediate feedback. Crucially, at the exact same time that acknowledgement is sent back, the main application thread hands off the actual work, the computationally intensive stuff. Embedding the query, doing the 2 database lookups for single source retrieval, calling the OpenAI LLM for generation, it passes all of that off to be executed by a dedicated FastAPI background task.
So the main web server process, the thing talking directly to Slack, is immediately freed up. It doesn't block. It can handle the next incoming dvask query right away. And the user isn't left hanging, staring at a waiting message in Slack for the full API call to complete.
Precisely. That background task now churns away asynchronously, completely independent of the initial request-response cycle with Slack. It takes its time, 5 seconds, 10 seconds, however long it needs to perform the full RAG pipeline correctly, when the RAG process finally finishes and generates the actual answer.
How does that answer get back to the user in Slack?
The background task then uses the Slack API again, but this time using a different method, probably a webhook URL that was included in the initial /command payload, or maybe looking up the original message context to send a new message containing the final well-formed answer back into the Slack channel, often posting it as a reply in a thread under the original dvask command message.
So it appears a few seconds later as a separate message from the bot.
Exactly. It's a seamless, asynchronous flow from the user's perspective. They ask, get instant acknowledgement, and then a few moments later, the answer pops up. This approach made the chatbot both highly accurate, thanks to single source retrieval, and functionally usable within the constraints of the real-world workplace environment they needed it in Slack. Without this specific architectural choice to handle the processing asynchronously, the chatbot, no matter how smart, would likely have been unusable in Slack due to the timeout issue. Hashtag outro.
Wow. Okay, this deep dive into how Taranis built their internal ARG chatbot It really does provide a pretty complete blueprint, doesn't it? For solving that pervasive internal knowledge chaos problem. It covers the whole life cycle, really, from figuring out the right data ingestion strategy, choosing the tech stack, refining accuracy with metadata and custom retrieval, all the way to deploying it accessibly for users in Slack. If we were to summarize the absolute crucial steps for you, the listener you know, someone who might be thinking about implementing something similar in their own organization, what are the most non-negotiable critical takeaways from this whole process?
Yeah, I think the roadmap they laid out is built on maybe 4 core pillars that really move beyond just the basic ARC theory and get into successful production engineering. First, fundamentally, you have to recognize that ARG architecture itself is pretty much the essential and certainly the most cost-effective path forward for grounding LLMs in your own private internal data. Forget about trying to constantly retrain these massive models. It's just not practical for most orgs. RED is the way.
Okay, RED first. Pillar 2.
Second, choose your production stack very deliberately. You need to graduate quickly from just local testing tools like maybe ChromaDB and move to scalable, enterprise-grade managed vector stores. Something like MongoDB Atlas Vector Search, which they used, leveraging its features like optimized HNSW indexing, metadata filtering, and crucially, the operational support and reliability that comes with a managed service. Don't skimp on the vector database. It's foundational.
Got it. Production-grade vector store. Third pillar.
Third, the strategic use of metadata for domain filtering is absolutely non-negotiable if you have knowledge spanning different teams or topics. Adding tags like domain, warrant to port product during ingestion, and using pre-filtering during search is essential to ensure relevance, prevent that cross-departmental context contamination, and ultimately make the system trustworthy for users. They need answers from the right knowledge pool.
Makes sense. Metadata is key. And the final pillar, the big innovation.
And finally, I think the most insightful takeaway is recognizing that naive retrieval often fails in subtle ways. The really clever innovation here was their custom single-source retrieval method. Designing that 2-step process, find the best chunk, then grab all its siblings from the same source document using metadata that ensures the LLM always receives a cohesive, high-quality, complete document context. It required custom coding, yes, and maybe a tiny latency trade-off, but they correctly prioritized answer accuracy and coherence over marginal speed gains. That focus on context quality is huge.
It really hammers home the point, I think, that building these sophisticated internal AI tools today doesn't necessarily mean you have to build everything from absolute scratch.
Yeah.
This Taranis project, it leveraged fantastic existing open source tools like LangChain. They customized them just slightly where needed by inheriting and overriding core methods, and then they integrated them tightly with powerful cloud services like OpenAI and MongoDB Atlas, and used smart API frameworks like FastAPI for the deployment glue. It's really a perfect demonstration that these challenging internal documentation needs can be met efficiently by adopting this specific blend of LLM intelligence and targeted pragmatic data engineering.
Indeed. It really proves that often the most challenging parts aren't the core AI models themselves anymore. Those are becoming almost commoditized via APIs. The real differentiator, the hard work, is often in the data engineering required to effectively connect, clean, process, and retrieve your unique proprietary information, especially when you're managing diverse and messy sources like Confluence, code repos, and chat logs. And if we connect this right back to those challenges they faced, particularly with integrating the conversational data from Slack, that issue of detecting and managing outdated conversations is just so critical. We talked about how simple timestamping isn't quite enough and how you'd likely need some kind of temporal ranking algorithm. This raises a really interesting, maybe final provocative thought for you, the listener, to mull over.
Okay, leave us with something to think about.
Given how hard it is to keep conversational data relevant and how quickly technical documentation itself can become obsolete, how might future RA systems evolve beyond just manual curation or simple timestamp checks? Could we see systems that automatically detect and deprioritize outdated or deprecated knowledge sources during retrieval, not just by looking at a timestamp, but maybe by integrating other signals, perhaps analyzing user feedback on answers, was this helpful? Or checking for deprecation tags on linked tasks in Jira or GitHub issues, or even calculating some kind of inherent knowledge decay score based on how often a document is referenced or updated. Could this happen without needing constant human intervention and manual retagging during the ingestion phase? That challenge of automated, real-time knowledge decay management, that feels like the next great frontier in keeping these internal RD systems truly current, reliable, and trustworthy over the long haul.